Today on this recorded video, I'm going to talk about series resistors that, similar to the example that we did last time with parallel resistors, series resistors where they're all in a line, and how to calculate the equivalent resistance in that case. Then I'm going to jump into the physics of solar cells, which takes us from what we were talking about regarding energy, and then I'll talk about some practical considerations using solar energy, since I think it is such an important field and it's related to physics, so I want you to see it here, and it ties in perfectly well with the agenda that we've had so far. So the first topic is equivalent resistance and series circuits, and I want you to think about this for a minute. Think about two resistors in series. In this case, I'll make them 6 ohms, but I mentioned that when you have resistors in series, to find what we call the equivalent resistance, you add them together. And I'll show you why in a separate video where I can actually write things out. But given that, and of course the current through the resistor, through any resistor is through the entire circuit in this case, is going to be the battery voltage divided by the equivalent resistance. That'll tell you how much current is flowing through everything. And it has to flow through everything because it's a series circuit. It's easier than the parallel case in order to make sense of this. In the parallel case, you had multiple different currents. Here you just have one. And again, the current through all of them is the same, but the voltage can be different depending on the value of the resistance. And you're going to see that both on this video and in the example we do in class. So for practice, consider a 12-volt battery that's connected to two resistors that are both 6 ohms that are all in series. Please find the voltage dropped across each resistor, the current through each resistor, the power that's consumed by each resistor, and the energy that each resistor would use over a one-day period. So it's all similar to what we did in an example from the other day, but this is practice with this series circuit. See what you can do with that. And there's the answer to it. Each resistor is going to have the same voltage drop across it, which makes sense because they have the same size. One way to do this problem would be to find the equivalent resistance of this series circuit here. Since they're two 6 ohm resistors in series, the equivalent resistance you'd get by adding the two of them together, which gives you an equivalent resistance of 12 ohms. Well, if you have 12 ohms connected to a 12-volt battery, 12 volts divided by 12 ohms gives you 1 amp. And so that actually gives you the answer to part B. Each resistor has 1 amp flowing through it. Well, if you multiply 1 amp times 6 ohms, that means that each resistor has 6 volts dropped across it. And of course, if you add 6 plus 6, you get 12, which you should. They should both add up to the voltage of your power supply or your battery. And we could then calculate the power consumed by each resistor. You take 6 volts, multiply it times 1 amp, and you get 6 watts. Multiply the 6 watts times 24 hours. That gives you the number in watt hours, 144 watt hours. Yes, you could do it in joules, but you'd get a much bigger number. Or you could say it's 0.144 kilowatt hours. By dividing this by 1,000, that'll give you the units for kilowatt hours. Okay, and this next example you'll do in class, so I'm not going to go over that here. We'll talk about it there. I'm going to jump into the physics of solar cells. Solar cell. So I'm sure you've heard of them. They basically take the energy, the light energy from the sun, and they convert it into electrical energy that you can use to do stuff with. Which is, I think, just such a fantastic idea because we have plenty of sun, right? There's also, of course, costs associated with doing this, environmental costs and things like that. But once you have them, they last for years and years and can be doing this conversion for a long time. So overall, they're a net benefit when we're having to consume a lot of energy, which we do. And the basic material used in in solar cells is one of the elements on the periodic table called silicon. And silicon is a semiconductor, which means it's not as good a conductor as a metal, Like if you put your two leads of a meter on it, you're not going to get the beeping sound that you get when you put them on two pieces of, when you put them both on a piece of metal. That's the same piece of metal. And we're going to talk about, in the process of doing this, different energy levels associated with silicon and the photon. The photon is, of course, one way you can think of how light energy is transmitted. And we'll talk about the fact that we actually purposefully make the silicon slightly impure. We put things in it to make it a little bit contaminated, but we do it in a very controlled fashion, with two different types of contamination, which I'll talk about. We'll get into electrons and their opposite holes. They're not electrons and protons, they're electrons and holes, where the hole is an absence of an electron. We'll get into something called the p-n junction, which is associated with transistors and semiconductors, and also with solar cells, which were discovered, the modern version of the photovoltaic solar cell basically was discovered at the same time as the transistor in the late 40s, 1940s, I should say. And we'll talk about different types of currents, which is the motion of charge that are associated with solar cells and how they come about. So there's some really good sources if you want to dive deeper into how solar cells work. And I'll provide these on a PowerPoint slide for you if you're interested. We can only go so far into it in the time we have, but I want to give you a taste for how they work. So as I said, semiconductors sometimes behave like insulators, sometimes behave like conductors. They're kind of in between. When things are conductors, that means the electrons can roam freely. When they're insulators, the electrons are stuck where they are, and they don't move around, which means you can't really get a current passing through them. Semiconductors can behave in both ways depending upon the conditions. And usually when we talk semiconductors, we think of silicon as one of the most common ones. But there are other materials that can also act as semiconductors besides silicon. And it's really interesting how solar panels are made. We actually have to melt silicon and the idea is to create a single crystal of it. And so there's processes to do this. And they're actually melted into a certain shape. And depending upon how they're contaminated, we contaminate them. Silicon, if you look on the periodic table, has 4 valence electrons. So what we actually do is we take some of the wafers of silicon we create and we contaminate them with atoms of boron. And boron appears right here on the periodic table. It's one row above and one column to the left of silicon, which means that instead of having 4 valence electrons, boron has 3, so it has 5 holes. Phosphorus, on the other hand, is one up from silicon on the periodic table. So the other wafers of silicon that are interleaved between different contaminants, you have a boron contaminated one, then you have a phosphorus contaminated one next to each other. The phosphorus has 5 valence electrons, so it actually has 3 holes. So you have this interesting situation where you have a wafer here that occasionally has a boron atom, so it has this extra electron sitting there. Then you have this area here of phosphorus, which has one less atom in the valence. And so, one more atom in the valence. So what you have is the stuff on the phosphorus, the electrons in the phosphorus want to migrate to the boron, and the holes in the boron want to migrate to the phosphorus. So you get this sort of diffusion that happens of the electrons going from phosphorus to the boron, doped silicon, and the holes going from the boron to the phosphorus. And so you have this sort of region that has this drift happening over a small distance as a result of this distinction. That's what a semiconductor is. And then on top of that, once you have this drift there because of diffusion, they actually don't want to stay there because they're actually, even though there's an extra electron and an extra hole on one side, they're electrically neutral. But when they start migrating this way, then they're no longer electrically neutral. So you have these two conflicting forces: the diffusion force that pushes them this way, and the electric force that wants to pull them back, We'll be talking more about the electric force later in the semester, but that gives you an overview of what the situation is like in a semiconductor. And there'll be another slide that says a little bit more about that in a few minutes. But this tells us about how they're doped here on this slide that we already discussed a little bit. And this tells us a little bit about how the silicon is melted and created this beautiful looking large crystal of silicon. And people have to actually do this in a very clean environment. So it's quite a job making solar panels. And this is kind of a molecular map of how the different atoms are bonded together in silicon, which is similar to carbon, germanium, and other semiconductors, as well as other different combinations of, this is a compound, gallium arsenide, which is also used in some solar panels. So there's different types of solar panels, but notice that the crystalline structure is very similar in both of them. And we actually identify whether they're doped with what's called N-type, which would be with phosphorus, or P-type, which would be with boron, just by the shape of how the wafers are cut. That tells us how they're created. So it's kind of just a way that we use to identify, is this an N-type or a P-type piece of semiconductor? Again, N is doped with phosphorus, P is doped with boron. You don't have to memorize that, but it's something interesting and useful to know. And then what's interesting about solar panels and solar cells, there's something called the photoelectric effect that you might have heard about in chemistry. That's basically the idea that photons, which are what light is comprised of, if they hit a certain material and there's enough energy in that photon, they will cause an electron to be released from that material. That's something called the photoelectric effect. And that's what actually causes a current to occur in semiconductor materials, which we'll talk about. It happens actually in metals. If you have light hitting a metal, we'll get this photoelectric effect occurring. But it turns out that it's the frequency of light. The higher the frequency, the higher the energy of the electron that gets released. And the more light, the brighter the light, the more electrons get released, as long as the light is of a high enough frequency, a high enough energy. The higher the frequency, the higher the energy. That is how we create electric currents, essentially. And the brighter the light, the more electric current you're creating. So you want your solar panels to be catching the brightest light of the sun, if at all possible. That's why some solar panels actually steer. If you ever look at the solar field, the solar panels actually are on little timers that make them track the sun so that they get the most energy possible from the sun. So I'm going to complete this video, and there'll be a subsequent video that keeps talking about solar panels, a little bit about their physics, and how to practically apply them, and look at issues of efficiency to figure out how many solar panels you'll need for a given situation.